So this is the last module of the course, and we would review a typical CMOS process flow. In this one, you are looking at a process where you create your gate first using polysilicon gate process. Nowadays, the advanced CMOS devices, especially those used for making microprocessors and DSP, digital signal processors, use metal gates and high-K. That process is slightly more complicated in the front end of line, and also there is this FinFET process, so we would not look at those. The differences are mostly in the shape of the device. So a FinFET is a 3D device. So obviously making all these figures is a little bit complex, and then you may also have to visualize in your mind how the device looks like. But the process flow is similar because you are trying to make a MOSFET, or in fact two types of MOSFETs, right? And then once you make the MOSFETs, then you are actually making connections between these MOSFETs to wire up integrated circuits. In fact, several types of circuits that you can imagine from digital circuit theory. For example, you start with inverters, and then you use different kinds of inverter configurations to make NAND gates, NOR gates, and then use these universal gates for making adders, subtractors, and all kind of other digital circuits. Okay, so the whole process flow is kind of divided into two parts. One is called the front end of line, and that is where you make the transistors, and then the next part is called a back end of line. Okay, so when we finish off the front end of line process, we would actually discuss some of the features, and then we will go on to the back end of line process. I would like to acknowledge my former colleagues from IMEC, Inter-University Microelectronics Center at Leuven, Belgium, for teaching me silicon process and device integration. I spent about 5 years there, looking at, first of all, the integration of fully silicylated gates in planar MOSFETs, and then I started working on FinFETs, the integration and integration of metal gates and high-K in FinFETs. Now, this is something that you have already seen. So if you take an IC and then cut this up and look at it using an SEM, you would find the image that you see on the left hand side. At the bottom of this, you can actually see these tiny little transistors. Okay, on the right hand side, you have a blown up image of the transistor, and where you can see the right hand side bottom cross section TM image, transistor with silicon at the bottom, right? And then you have source drain on the left and right ends of this, and then you see this L-shaped features. These are the spacers, and between the spacers come the gate. Okay, and above the transistors you see this kind of rectangular blocks that are going up many layers. So in this you can actually count 6 layers, and these are metalizations for connecting these transistors together to make circuits. And here you see how we start the processing of the transistors, and the process steps are actually shown using 6 figures. So you can see these numbers 1, 2, 3, 4, 5, 6 that indicate the sequence. Typically you start with a silicon wafer, which is these days 300 millimeter in diameter, so that is 12-inch in diameter, right? And then the wafer type is typically P-type, because that is less expensive compared to N-type wafers. And we had discussed previously that you may actually grow an epitaxial silicon layer on the top, which gives a very high quality silicon, and on which you make your devices. So the transistors can take at the most a few micrometers of silicon, the top layer. Okay, so that is typically grown using epitaxial process. And the lower part, the starting wafer, is usually CZ, so that is a Chetrzasky silicon grown wafers, right? And this process, when you actually want to build this integrated circuits, what you do is you buy these wafers where epitaxial silicon deposition is already done. Okay, so we would refer to this wafer as the silicon wafer, but keep in mind that usually they have on the top part the silicon is epitaxially grown, so that you get a high quality silicon. So the first step would be a cleaning of this wafer. So you use the RCA cleaning, which we have discussed previously, and in fact all of these processes were discussed in previous modules. So you take this wafer and then do a cleaning. So essentially you remove all kind of contamination from the wafer surface, and you grow a silicon dioxide, which is called a pad oxide, and this would be approximately 15 nanometers. All these numbers can vary from one technology node to another, and maybe from even one company to another. So all these numbers are typical numbers. So what is the role of the pad oxide? Okay, so this is grown by thermal oxidation of silicon, and this is deposited so that the next layer that is coming on top, so that is the silicon nitride, which can create a stress on the silicon. So this is something used as a buffer or a pad between the silicon and the nitride. And after the silicon oxide is grown, you deposit silicon nitride, which is typically about 150 nanometers, and this is used an etch top layer for chemical mechanical polishing. Okay, so this is again we'll see as we go ahead. And typically you use thermal CVD processes so that you get stoichiometric high density silicon nitride. And then you do an active area lithography, okay, and you use the reactive ion etching to etch a trench. Okay, so typically this trench is about 400 nanometers deep into silicon. Okay, so you need to etch the 150 nanometer of oxide, and then 150 nanometer of the nitride, 15 nanometer of pad oxide, and then 400 nanometer of the silicon. As I mentioned before, all these numbers will depend on the technology node, okay, and the particular manufacturer, yeah, and their device designs and so on. So we are not going to discuss or dwell into details, because many a times this is proprietary. So first and foremost, we may not know. So these are numbers that I am familiar with from my IMEC experience. Okay, so you etch the trenches. So usually the sidewall is not vertical as shown here, slightly slanted, so you will see that on the next slide. And then you remove the photoresist, right? And then the wafer is again subjected to an RC, essentially to prepare the exposed silicon surface for growing a very good quality silicon dioxide. You can see that on the side, on either sides of the trench, you have the silicon, right? You are going to build your transistors on top of it. So the trench side walls would be part of the transistor in some places. So they should be actually passivated with very good quality silicon dioxide. So what you do is to grow a thermal oxide, typically about 20 nanometers at very high temperature, typically 1100 degrees centigrade, and you use pyrogenic oxidation so that you have the viscous flow of the oxide during the growth. So the corners of the silicon are rounded. And then you deposit, so this is referring to figure 4 in this slide, on the slide. So you deposit a silicon dioxide by a high density plasma deposition. So this has to be about 550 nanometers, okay, and this is a high density plasma oxide, and typically inductively coupled the plasma CVD process. So this would fill the trench by a deposition and etch process, right? So that you fill the trench without any gaps. And then you polish the silicon, the surface, so that you can get a flat surface. Okay. So this is achieved by mechanical polishing, which was discussed as part of the wafer manufacturing process. Essentially, you are, doing some mechanical polishing so that you can remove this thing, but you also add some chemical component in the etching so that you can actually get some selectivity between the silicon dioxide and silicon nitride. So you want to actually fill this trench with silicon dioxide but remove it from elsewhere. Okay. So if I use any other etch process, for example, if I use a wet etch process, it will etch from everywhere. And if I actually expose it to a plasma for etching silicon dioxide, it would etch the silicon dioxide vertically from everywhere. Okay. But if I use a CMP, so this is actually doing a polishing. So once the surface is smooth, it would not etch the thing much. Okay. So that is the idea, or you can stop the etching. So the CMP will be done, and the silicon nitride is used as an etch stop for the CMP process. Okay, so that is where the chemical component in the CMP comes into play, and you get a flat surface. And then you are going to remove this nitride also subsequently. So the silicon oxide may pop out of the wafer surface, right? So you do what is called an oxide recess etch by using hydrofluoric acid. Okay, so you etch after the CMP in step 5, you would actually do a small recess etch of the oxide using dilute hydrofluoric acid. So this would not etch your silicon nitride. And then you are going to remove your silicon nitride in hot phosphoric acid at about 165 degree centigrade. Okay, so you get silicon with trenches. The trenches are filled with high density plasma oxide, and then the silicon dioxide surface or silicon surface is actually well passivated with silicon dioxide, and this is what you get at the end of the shallow trench isolation process in your overall process flow for making the chip. Okay, so this slide shows you the wafer after the shallow trench isolation process is completed, and you can see the bottom part is actually bottom figure is actually an SEM cross section of shallow trench isolation, and you can see this the silicon substrate and the STI. So the STI regions are where you have the oxide. So something that they've actually shown is some interesting, that if you have a very narrow trench, right? So the aspect ratio of this trench seems to be 1 or larger. So the depth to width ratio, right, in the middle one. So that actually what they're showing is that they're not able to etch it as deep as the wider trenches. So this is called an RIE lag. This is because when you do the reactive unetching to etch the trenches, right, if the trench is narrow, then the etch do not proceed as fast as in a wider trench, because the reaction byproducts have to diffuse out, and this would be a slower process in a shallow trench or in a narrower trench compared to a broader trench. And you can also see the STI, the oxide corners at the top. So there is a step there, right, above which actually the top of the silicon dioxide is above the level of silicon. Okay, this is the next step. So you are trying to make both N-channel and P-channel transistors on the same wafer. Okay, so we started off with P-type wafers. Okay, so we need to create an N region, right? N region for making the P-channel transistors. But also, usually the doping of the wafer may not be suitable for your N-channel transistors, in the sense that the concentration of the dopants may not be the right one. Okay, so you would create what are called wells for making the two types of transistors. So you would create an N well, and also for making a P-channel transistor, and you would also create a P well for making the N-channel transistors. Okay, so what you would do is to create the N well, you do a lithography. So basically you spin coat the photoresist and then use a mask to expose the photoresist, and when you develop it, the resist would remain on the regions which you have designated as P well, and the rest of the wafer surface is exposed. And then you do the implantation, okay, of N-type dopants, typically phosphorus and arsenic, and usually you do 3 types of implants into it. So one would be a deep implant, okay, which would actually create the N well. Yeah. So this can be like, you want to go deep down to 300, 400 nanometers, right? So you would, and then you can imagine that if I just do one implant, I would have a strong profile, right? And the doping concentration in the well will not be uniform. So you may actually do maybe 2 implants or even 3 implants at 3 different energies. So you get 3 profiles, okay, which have the peaks, the projected range at 3 different depths, and if you add up the dopant concentrations, you nearly get a flat doping concentration in the well. Okay, so this is your N well implant. But then Next come your transistor design related implantation. So there's something called anti-punch-through implant in transistors. So essentially, when you apply a drain voltage to your transistor's drain, the depletion region that is formed should not encroach the whole channel length, right? And then go and meet the depletion region from the source side. So this would then be a punch through, and all the current would flow through this, and this region punch through cannot be controlled using a gate. Okay, so you want to avoid this, and the thing there is that you will actually create an anti-punch through or do an anti-punch through implant, so that the doping concentration at the drain source level in the channel region would be high enough so that you don't get any punch through. Okay, and then you would do the next type of implant, which would be used for getting a fairly highly doped surface layer in the channel region. Okay, which would be which is the right type of doping concentration for your threshold voltage. So threshold voltage depends on the doping concentration in the channel. Okay, so you would do this. So there are three types of implants, even though we call it N-type implants for in the N well. So there are three types. One is the well implants, which are P, and multiple implants, right? And then there is an anti-punch through implant, so that would be a medium range implant. And then you would do a shallow implant, which is used for controlling the threshold voltage of the devices. So once you do this N-well implant, you do a complementary thing in the other region. So what you do is you strip the photoresist, right, and then mask the N-well regions, yeah, and expose the P-well regions on the wafer by using a photolithography with an appropriate mask. And then you're going to do the P-type implants, so boron typically, right? And you would do there again the P-well implants, which are deep, and then you have the punch-through, anti-punch-through implants, which are medium energy, and then a threshold voltage implant. Okay, and then of course you remove the photoresist, so that is very important, right? And then you can optionally do an oxidation or high temperature annealing to activate the dopants, okay, that you have implanted. Okay, now you can see that if you go back to the previous slides, you remember we had the pad oxide that was used for stopping the CMP, right? Meaning we deposited the nitride on top of pad oxide in this shallow trench isolation. So that was still there when we did the implants, and then that has to be removed. So what you're going to do here is to actually create your gate. Okay, so remove that oxide which was already there, and you can see that when you have the oxide for at the time of implantation, what does it do? The oxide is amorphous, so when you do the implant through the oxide, you don't have channeling problems, right? Because when the implants go through the amorphous layer, they're scattered in all directions, right? Okay, so you remove this oxide, and then you are going to grow a gate oxide. So you need a very good clean surface. You do an RCA cleaning again. So this process is done again and again, RCA cleaning. And then you grow a gate oxide. Typically, done using thermal oxidation process. Again, as I mentioned previously, that we will not discuss high K metal gate process here. That is slightly more complicated. So, but you know what is used for this. For example, ALD used for depositing high K dielectrics. But that process is a bit more complicated. Okay, so we would not go into the details. If anybody is interested, I can provide you references to review this. So gate oxidation is done. So that's the thermal oxide, and then you deposit polysilicon layer, which is intrinsic, undoped, right, using low pressure CVD process. Typically, when you do this depositions, the low pressure CVD is done in a thermal reactor, okay, and typically you have the films depositing on the back side also. Okay, so that is what you mean by removing the backside layer. So you need to remove the backside layer. Then you have the gate lithography, and you will try etch polysilicon, and here we target to get a very straight 90-degree profile or vertical profile for the gate. Subsequently, you etch the resist. Okay, so the silicon might have got some damage at some places. Okay, so because that you have used a reactive ion etching, right, for the polysilicon. So you do what is called a re-oxidation. So this is actually seen to improve the gate oxide quality and the zero resistance and other things in the transistors. So essentially you do an RCA cleaning again, very important, and then you do a re-oxidation, essentially a very low temperature, about 700 degrees centigrade, 750 degrees centigrade for a couple of seconds. You go extremely thin oxide on the silicon wafer surface that is exposed to the plasma. Okay, so we got the gates on the N well and the P well. So we now need to do the implantation for making the source drain. Okay, but you also see this name halo implant. So what does it mean? So this is the halo implant is actually carried out for controlling the short channel effects in the very short transistors, very short gate length transistors. So what you do is, if I take the N channel transistor, so that is a P well, right, on the left hand side. So the channel region is supposed to be doped P-type. Okay. Now the problem with a short channel device is what? When you apply drain voltage, this would create a depletion region on the drain side, right? And the depletion region should not penetrate too much into the channel. Okay, so what you do is you take this device, right, with a gate, and then you do a tilted implant of boron. Okay, so 2 quadrants, if you remember. So this will be from a tilt from the vertical towards the left first. Okay, and then you are doing a boron implant. So some of this boron would actually go under the gate, at the left hand side edge. Now in the next quadrant, okay, the next half of the wafer, so what you're doing is you're rotating the beam towards the right, from the vertical, and then you do again boron implant. So that would create some meaning for some of the you will implant some boron under the gate. So at this corners of the gate, you have boron under the gate. So you can actually, based on the description that I'm providing, you can make drawings of boron constellation on the at the top of the wafer. Okay, and then you are going to do this. So the halo implants can be done at fairly high tilt angles. Okay, 45 degrees and so on are common, or 30 degrees, 45 degrees is a common. And then you do a source drain extension implants. It will be tilt of about 7 degrees to avoid channeling. Okay. So these are called source drain extension implants. So again, this should be very shallow implants to control the short channel effects. And this would be, for example, for a N-channel device, the shallow extension or source drain extension implants will be N-type. Okay, and then so typically it would be arsenic, and then you are going to strip the photoresist. Yeah, and then you do a rapid thermal annealing to activate the implants. Okay. And then the next step is you cover the N-channel devices, right? Because you want to do the same type of implants on the P-channel device as well. Okay, and then you do this halo implant, which is N-type, to introduce N-type dopants under the gate in the corners. Okay, and a P-type extension implants. Okay, source drain extension implants, and then you're going to remove the photoresist and do a rapid thermal annealing. Now, very important question for you is that why don't we do this process in sequence reverse, or actually, let's say we will do all the implants on the P-channel transistor first. Okay, so you see the two segments of process, right? One is the photo N plus, right? That group, 5 steps, and then the next group is photo P plus. So we are actually saying on this slide that you do the photo N plus, right? N-channel transistor implants are done first, and then P-channel transistor implants are done subsequently. Why can't we do it the other way around? That we do the P implants, right? The P-channel implants first, and the N-channel implants. Okay, so the thing is that if I am taking the N-channel transistor implants, okay, for the source drain, I would use arsenic. Okay, so arsenic being heavy, I would actually create a lot more defects, right? Homophisization of the silicon, and I need to anneal these defects, right? But now, suppose I postpone this anneal till the end of the slide, where I have already also implanted boron for the P-channel transistors, right? The source drain extension for the P-channel transistors. Now, the problem with that is that my annealing should not cause too much of diffusion of boron, because that would actually diffuse faster than arsenic. Okay, so I would really like to do a low temperature, very short annealing, but that may not be sufficient to remove the damage created by the arsenic implant on the N-channel transistors. Okay, so when in this process flow that is shown, the last rapid thermal annealing step is seen by both the N-channel and P-channel transistors. See the point? Both the boron implant in the P-channel device as well as the arsenic implant in the N-channel device will see the rapid thermal annealing step, the second rapid thermal annealing step. The first rapid thermal annealing step is seen only by the arsenic implant. So if I now put this P plus part first, right, and the N plus part next, then the last implant will be seen by the first boron implant, okay, of the p-channel transistor. So you would like to avoid this kind of situation. This is what you're trying to sequence the process to take into account the differences in diffusion of arsenic and boron, okay, which will influence the two types of transistors you're going to build on the wafer, okay, differently. So that's very important. So now we have the gate, the extensions, source drain extensions, and so on. So we would now create spacers, okay. So you are actually going to deposit dielectric layers. First would be oxide and silicon oxide, and then silicon nitride. So the silicon dioxide would be very thin. And why do you need that thin silicon dioxide layer? So you need it because, as I mentioned previously, the silicon nitride, when you deposit it directly on silicon, could create stress on the silicon. So you would like to avoid it. Okay. So you deposit a silicon dioxide layer, which is typically in the range of 10 nanometers. Okay, and then you would deposit a silicon nitride. Yeah, and the silicon nitride layer will be in the range of 50 to 100 nanometers thick. So this process, both these things would be done using CVD, typically thermal CVD processes in the past, and now more recently they also use PECVD processes for doing this. So if you're using a thermal low pressure CVD processes, then you would get this films deposited on the back side of the wafers also. So in that case, you remove the backside layers by wet etching. Now we have seen how the spacer is etched in a previous module, right? You are going to use an anisotropic dry etching to create the spacer. So you can see the gates, right? Polysilicon, and both sides of the gate you have the spacers, right? Now, what are you going to do next? Next, you're going to do the high density drain source implant. So that is called the HDD implant, high density drain. So essentially, the doping density in the source drain regions that you create by this implants will be fairly high. So this is rather straightforward. What you do is you're going to implant the N-type channel devices, N-channel devices first. So you would cover up the P-channel transistors and then do the N-type implants, typically arsenic. Okay, then remove the photoresist. You do an annealing, and then in the next step, you would cover up the N-channel regions, and then do the P-type source drain implants, deep source drain implants, and then strip the photoresist. Okay, and then again anneal. So next comes the self-aligned salicide process. Okay, so here what are we going to do? Actually, we are going to make contacts to the source, drain, and the gate of the transistors. So we have discussed the self-aligned salicide process in previous module. So you go back to your thin film deposition module when we discussed the sputter deposition. We had described this process. So what are you going to do? Actually, you take this vapor, right? You will clean up this vapor to remove any native oxide that is grown on the silicon exposed on the surface. Okay, and then you're going to deposit one of these metals, titanium, cobalt, titanium, or cobalt titanium mixture, or cobalt itself, or nickel. Okay, so more recent technologies use nickel, and then you're going to do a silicidation process. So what you're going to do is actually the silicidation is carried out in two steps, which is, for example, for nickel it would be a process around 300 degrees centigrade, okay, rapid thermal treatment, which will create a silicide, okay, by reaction of metal with the exposed silicon. So the metal will not react with silicon dioxide or silicon nitride, right? It will only react with silicon. And then you use a selective etch. What it does is the unreacted metal will be removed. So the unreacted metal is on the silicon oxide, which is shallow trench isolation, right? And also on silicon nitride, which is the spacer, and that will be removed by the selective etch. So this is typically a wet etch process. Again, you can go back to the module on the sputtering and can find more details about the chemistries used there. And then you do a second rapid thermal process where the objective is to convert the silicide to the desired phase. So if I take the nickel silicide process, first I would convert in the first RTP step, I would convert the the metal will react with the silicon to create what is called a metal rich silicide. Okay, so this can be Ni2Si. Okay, and then I'm etching the excess nickel, right, unreacted nickel, and then during the second RTP I'll convert the remaining, meaning the Ni2Si that is on the source, drain and the gate, into NiSi, the monosilicide, which actually gives very good contact resistance with silicon. Okay, so this process, so whatever we have discussed so far is called the front end of line process. Okay, so you've seen that in this, we have made the transistors, right? We first made the isolation, we made the two types of transistors, and then you already have the source, drain and gate, some metal deposited, right? So that you can in principle measure the characteristics of the transistor. So the transistors are ready. Okay, now, so this is called the front end of line process. Now you're going to bring in dirty stuff onto this wafer, for example copper and so on, which would diffuse very fast into silicon. So typically in a manufacturing line, the front end of line process is done in one part of the manufacturing line, and that's kind of segregated from the back end of line process. Okay? In the sense of physically segregated. The tools that are used would be in a different type of, meaning different clean room, and the wafers, once they go into the back end of the line process, right, that part of the clean room usually don't come back to the front end of line because of contamination issues. Okay, so next we will take up the back end of line process in the next lecture.